For each problem, draw a picture with one element for each integral. Find the area bounded by the curves. So for this problem, we'll do y equals x squared, y equals negative 2x plus 8, and y equals 0 by integrating with respect to x, and then also doing the same problem integrating with respect to y. So the first thing we should do is draw this picture. We don't need to have it perfect, but we should have a decent sketch. And we'll have y equals x squared. And then we'll have a line coming down. It's going to have a slope of negative 2 and a y-intercept. And it'll look something like this. And we know that y equals 0 is the x-axis. Now I need to tell you this one right away. Y equals 0 is one of the hardest ones because people, for whatever reason, will confuse the two axes. So you just got to make sure that you check that y equals 0, yes, at every point on the x-axis. Now we need to set this up. When we're looking at this, we have the parabola and the x-axis. But if I draw my element, my rectangle that I'm summing up, when I get to this point here, there's a different curve on top. So what does that mean? That means I'm going to need to have two separate integrals. I will need to find this point right there, the intersection point of these two curves. Now sometimes we can do it fairly easily, and most people will call that by inspection. That basically just means by looking at it. We can say, where does x squared equal negative 2x plus 8 at x equals 2? If that wasn't so clear, what we could do is say that x squared equals negative 2x plus 8. So x squared plus 2x minus 8 equals 0. X plus 4, x minus 2, x equals negative 4 or 2. We're in the first quadrant here, so we want the positive 2 value. Now we have, when we're looking at this, this is basically the same as we've done before. We'll have the top curve minus the bottom curve, and that is x squared minus x. So let's set this up. We'll go from 0. That's our starting place where we're summing it up. We can move this rectangle starting here all the way up to this spot, and that will be the same way it's found, the x squared minus x. So we're going from 0 to 2, and we can just say x squared dx plus that second one from 2 to the x-intercept of the line, which will be 4, of this time it will be negative 2x plus 8, and then dx. And when we're sliding along the rectangle, everywhere in this section from 2 to 4, it's always the line minus the x-axis. And we could write it as x squared minus 0 and negative 2x plus 8 minus 0, but we don't need to. Let's slide this up a little. We can find the antiderivative, x cubed over 3, evaluated from 0 to 2, plus negative x squared plus 8x, going from 2 to 4. Plug it in, we'll have 8/3 minus 0, plus negative 16 plus 32, minus negative 4 plus 16 when we plug in 2 into there. And we can simplify that and we'll get 4 here and then 8/3, and that will give us 20 over 3 square units. And that's it. Now let's take a look at the exact same problem. So let's re-sketch our picture. This time we're going to go with respect to y. Oh, I forgot to label over here delta x and delta x. So let's go and do that. I thought about it and I didn't say it. Over here we'll have a rectangle this time. Since we're going with respect to y, the rectangle is going to be perpendicular to the x-axis, or it's sliding along, perpendicular to the y-axis, or sliding along the y-axis. So let's take a look. How will I find the area of this rectangle? Well, I have my thickness. That thickness is my vertical length here, and it's going from a starting value down here at y equals 0 all the way up to this point. Now, what's the coordinates of that point? We know the coordinates are 2, 4. We want the 4 because we're starting at y equals 0 and we're going to y equals 4. Since this is going to be integrating with respect to y, our integral will be dy, and all of our numbers need to be in terms of y. What's nice about this one is we only need one integral in order to do it. So we'll have the integral from 0 to 4, again, we're starting at 0, going all the way up to 4, and we calculate, it's going to be right minus left every single time in here. So the right curve is y equals negative 2x plus 8, but we need this in terms of y because this is the x value here. It's x on the right side minus x on the left, so we need to solve this for x, so we'll subtract 8 and then divide by 2, so we'll have negative 1/2 y plus 4. Let me move this down a little bit, equals x. Now on the other side, we'll have y equals x squared, x equals plus or minus square root of y, and we need to determine which one do we want. Do we want the positive or the negative? Well, this is the positive half. The negative would be over here, so we're going to say square root of y. Now we can set up our integral, and we'll go 0 to 4. Our right side is the line, so it will be, and just so the negative's not in front, I'm going to write the 4 first. So 4 minus 1/2 y, and then we'll subtract the left curve, which will be square root of y, and we're going to integrate with respect to y. To find the antiderivative, this will be 4y minus 1/4 y squared, 1/2 of y squared over 2, and this is y to the 1/2 power, so we'll add 1 to that, 3/2, and it'll be divided by 3/2 or multiplied by 2/3, and we're going from 0 to 4. Now we'll have 16 minus 4. Now we're going to have to say 2/3 minus 2/3 of 4 to the 3/2, and then we're going to go minus 0. How do we simplify 4 to the 3/2? Well, that's the same as 4, the square root of 4, which would be 2 cubed. So that will be 8. And then we'll multiply that by the 2/3, so we'll have 16/3. 12 minus 16/3 would be 36 over 3 minus 16, which will be 20 over 3 square units. Let's look at problem number 2. This time we're going to take this problem, find the area bounded by y equals 1/2 x and x plus y squared equals 8. Let's set up our xy axes. Y equals 1/2 x. We have a flat line coming through here. And the next one we can solve for x to say 8 minus y squared, or if you'd prefer, you could say negative y squared plus 8. Either way, it's whatever your preference. Now, negative y squared, we're going to be dealing with a parabola that's opening left since it's negative, and then it's shifted 8 units. This time, since it's along the x-axis, it's a positive 8. It's going 8 to the right. Now, I didn't put a scale on here, and that's okay. I'm just going to call this value right here 8. So I have some positive parabola. Now, when we're looking at this, we want to see, what do we want? Do we want a dx integral or do we want a dy integral? How do we determine that? We need to look at our rectangle. If I put a rectangle that is vertical, what happens? Well, we have the line minus the parabola, and that's fine. Line minus the parabola. But right after this point, what happens? You have this, the top part is the parabola, and the bottom part is the same parabola. That's not a nice situation to deal with. Sometimes we can solve it, but most of the time we want to say, forget that. Let us deal with the other way, a horizontal rectangle. Now let's slide it up and down in our region. It's the parabola minus a line, and it's consistent throughout the entire region. That's the way we want to do it. So we'll label this as delta y. Now we need to do what? We need to solve this equation for x. Well, the parabola will be x equals 8 minus y squared. We've already done that. And if we take the line and solve it for x, we'll get x equals 2y, multiplying both sides by 2. We're going to need our limits of integration. We need to find where do these two curves intersect. Well, we have x plus y squared equals 8, and we know that x equals 2y, so we could say 2y plus y squared equals 8. We'll have y squared plus 2y minus 8 equals 0. Y plus 4, y minus 2. So we'll get y equals negative 4 and 2. So that's saying this lower value down here is going to be at negative 4, and the upper value is at 2. Note, we could have done it with x's. We could have said y equals 1/2 x squared and plug that in, and we would have a quadratic equation. We could solve for x and then figure out what the y values are. I think it's fairly simple to do the y values first, though. So we'll have negative 4 to 2. My right curve is 8 minus y squared minus the left, which is 2y, and then times dy. So let's check. That's this length here. We have right minus left, and we have the thickness, delta y. We sum all of those up, find the limit as the thickness goes to 0, and we get our integral. Now we just need to integrate this. So this will be 8y minus y cubed over 3 minus y squared, going from negative 2 or negative 4 to 2. Let's see, this will be 16 minus 8/3 minus 4 minus the quantity, negative 32. And then it's going to be minus a negative 64, so that'll be a plus 64 over 3, and then minus 16. Let's simplify all of this, and we're going to get, let's see, we'll have 12 minus 8/3 minus negative 48 plus 64 over 3. This is going to make it a positive 48, so that will be 60, and then minus 64, and 8 would be 72 over 3. That's the same as 24, and so we'll get 36 square units. Almost ran off the page on that one. So to recap it, what's going on? The first thing we did was we graphed it. Our tendency is to have it as a delta x. So we look at a vertical, but we found there was a problem right here because the top and bottom curve were the same curve. So we switched the rectangle. It was going sideways. It's now the thickness along the y-axis, so it's delta y. We found each curve in terms of y, solve for x for each one, so it's right minus left, and then found our limits of integration, and at that point it's fairly straightforward. Find the antiderivative, plug in the lower and upper limits, and subtract. And that is all.